Hello everyone. We will now begin our lecture on chapter 9.3, which is on modular arithmetic. And this is the only section that we have in our syllabus from chapter 9. Now, modular arithmetic concerns with the remainder in a division. All right. The remainder in a division can prove very useful when we work with applications of a cyclical nature, all right, things that happen in a cycle. For example, the days of the week appear in cycles, right, over the month. So we start from a Sunday and then go all the way up to Saturday, and then Sunday starts all over again. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday again. So the days of the week occur in a cyclical fashion. So if we were asked, for example, if today is a Friday, what day of the week would it be 60 days from today? Right? So to answer that kind of question, we will be using modular arithmetic, and using the module techniques of modular arithmetic, we will be able to answer that type of question very quickly. All right? So that's what this chapter is going to be about. So these are the two main things that we are going to learn in this section of the chapter. Upon completion of this section, should be able to solve problems involving modulo M system. So we will learn what a modulo M system is and how to solve specific problems using the techniques of modulo M. And then determine whether a mathematical system defined by a modular M system is a commutative group. Commutative means that they can go back and forth. All right. So, for example, 4 plus 8 is the same as 8 plus 4, right? So that's commutative. It satisfies the commutative property. So we are going to see if a mathematical system based on the modulo M system is commutative or not. Now I would like to start with a brief introduction of the modulo M system, which is a common terminology used in modular arithmetic. Okay. Now in the modulo M system, or in any modular arithmetic, the answer, the solution that comes out of a modular operation is the remainder obtained from a division. All right. So in a modular operation, or in any modular operation, the result or the solution is the remainder from a division, and that is what our solution is. So in a modular operation, we are performing a division, but we are not interested in the quotient as we commonly are when performing a division. We are instead interested, or we are looking for the value of the remainder. So modular arithmetic, a mod operation, is essentially the remainder of a division. And now, what are we dividing by in the process of division? We are dividing by the M in a modulo M system. So M can take any integer value, and we divide a particular number. It could be any integer number. We divide that by whatever value this M is in the modulo M system, and then we look for the remainder, and that is going to be our solution of that operation. Now the solution will take certain values. So here it says in a modulo M system, the solution will be values from 0 through M minus 1. Okay, again, keep in mind we are looking at the remainder here, and in a correctly performed division, the remainder will always be less than what you are dividing by. So in this case, m, that's the number that we are dividing by, the remainder must be 1 less than whatever the m value is. And when I say the remainder must be, what I mean is the highest value of the remainder, the highest value that a remainder can take can be 1 less than whatever m is, correct? So 0, it can be, we can get a remainder of 0, right? Or we can get a remainder 1, 2, 3, and it keeps going. But the highest value that a remainder can be is m minus 1, right? So in a modulo m system, the solution will be values from starting from 0 up to m minus 1. And as we go through the number line, and I'm going to use this horizontal line here as a number line, and we are going to perform some divisions with a certain modulo m, and we are going to record the results, which are going to be remainder values, and we are going to see that those remainder values will keep repeating in a cycle as we perform the division along the number line. So what I'm going to do here is, this horizontal line is already drawn. I'm going to scale it with values. So let's make the middle value a 0, and then a 1, 2, 3, 4, 5. On the right hand side we have positive values, and this keeps going on. And then to the left of 0, let's mark negative values. So -1, -2, -3, -4, and so on. -4 and so on. All right. Now, based on this particular property of modulo m systems, remember that the solution set of the modular operation can take values from 0 through m minus 1. So if we are working with a modulo 3 system, all right, then the possible values that the possible values that the solutions can take could be a 0, it could be a 1, or a 2. All right, these are the 3 values that we can come up with as answers after we perform the modular operations. All right, it has to be the highest value, keep in mind again, will be less than whatever this m value is. All right, so I'm going to go ahead and perform division of these values on the number line and record the remainders up on top. And we will also see how the values 0, 1, 2 will repeat cyclically. All right, so I'm going to start with using 0 as our first divisor. All right, so well, the divisor is going to be 3. We are going to divide by 3 because that's the value of m, correct? So let's do the division here. Let me find a place here. All right, so I'll start here. Maybe 0 divided by 3. All right, so 3 times 0 is a 0. So we write the 0 here. What is the remainder? It's a 0, right? So over here, all right, so these are the remainder. I'm going to record the remainders here. Now we have to work with 1, so I'm going to do 1 divided by 3. 3 goes into 1 0 times, so 3 times 0 is 0. What is the remainder? 1, correct? This is the remainder. So I'm going to write 1 over here. Now we'll take the 2 and divide it. So let's work it here. 2 divided by 3. Again, 3 goes into 2 0 times. Record the 0 as the quotient. 3 times 0 is 0. What is the remainder? Remainder is 2. All right, so I'm going to record the remainder here, 2. Next number here is a 3, correct? So 3 divided by 3. 3 goes into 3 once. 3 times 1 is 3. Subtract. What happens to the remainder? Remainder is 0. All right. 4 divided by, now we'll work with 4. 4 divided by 3. 1 times 3, remainder is 1. All these are the remainder values, 1. And then if you keep going, if you keep performing the division, 5 divided by 3 will give us a remainder of 2. So as you see that these values are occurring cyclically, 0, 1, 2, 0, 1, 2. If we had a 6 here, we would again get 0 for 7, 1, 2. So the values, the values from the modular operation appear cyclically. On the left hand side with negative values, you will see the same occurrence. It will be 1 for negative 1, 2 for negative 2, and then again 0, 1, 2. All right, so that's what we mean when we say that the values will repeat in a cycle. So keep in mind, whenever we are working or thinking in terms of modulo M system, we are concerned with the remainder of, or remainder from a division by M of a certain value. All right, so we'll go further into this, and we will also look at different examples and learn how to perform different operations in modular arithmetic. So let's review one more time what the modulo M system is about. In a modulo M system, or in any modular arithmetic, the solution that we are looking for is a remainder obtained by performing a division of a certain number by the value of M. And the solutions can take values from 0 through m minus 1. So there can be m number of solutions, but the specific values that the solutions can take would be anything between 0 and 1 less than whatever m is. Now we can use the modular values. All right, we can use the values from a modular system and perform different binary operations, as we will see shortly. We can perform addition, subtraction, multiplication, as well as division. Now here's an example of the modulo 7 addition. Now when we say modulo 7 addition, the m of modulo m will be the 7. So this is going to be the value of m, because previously we said we call it the modulo M system, and we said that the modulo M system consists of elements from 0 to m minus 1 and a binary operation. So binary operation would be the addition, subtraction, multiplication, and so on. All right, so here m is 7 in a modulo 7 system, and the operation that we are talking about is an addition. So over here in this clockwise fashion, we see the days of the week represented starting from Sunday. All right, so we have 7 days in a week, so we write them around in a clockwise fashion. So Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. So Sunday is going to represent 0. All right, Monday is a 1, 2, 3, 4, 5, 6, and we stop at 6. After 6 we start again from 0. Right, even though there are 7 days in a week, because we are starting the numbering from 0, we will end at 6, and that is why we said we have m minus 1. So our numeration starts from 0 and ends at m minus 1 in any modulo m system. So what they've done here, you can see this is exactly what they have done. They've replaced the days of the week with the numbers, and over here they've created a table. All right, and this they are adding here. You see the elements along the top horizontal line is 0, 1, 2, 3, 4, 5, 6, and along the column here, the first column to the left, we also start from 0 all the way to 6. And when we add 0 plus 0 is a 0, 0 plus 1 is a 1, 0 plus 2 is a 2, and so on. So that covers all the additions in modulo 7 system. All right, so we will be applying rather this table to some of the problems that are going to come up, all right, as we progress through this. I'd like to spend a little more time on this particular slide and explain what the modulo M system implies, and also um, give you an idea of what kind of application this kind of mathematics, this kind of arithmetic may be used for. Now, the modulo system, or the mod operation, is just like the addition, subtraction, multiplication, and division operations in math, right? However, the mod operation gives as an answer the remainder from a division, right? So the answer from a modulo operation is really the remainder from a certain division. But what is the division by, first of all? The division is by the value of m in the modulo m system. So if we are talking about modulo 7, then the value of m is 7. So the answer from a modulo 7 system will be a number, any number, mod 7. All right, we do not use the word division or the sign of division. We say mod because we are interested here in finding the remainder from a certain division that we perform. All right, so some number mod 7 is whatever the remainder from a division is. So let's, for example, take the value 60. So 60 mod 7 will be the remainder after performing this division, 60 divided by 7. So let's perform that division. 60 divided by 7. So 8 sevens are 56, minus, we subtract, so 60 minus 56 is 4. So the answer for this problem, which is 60 mod 7, is really 4. All right, you don't concern yourself with the quotient. We are just concerned with the remainder because we are performing a modular operation. So I'm going to write here 60 mod 7 is a 4, which is the remainder, all right, from the division. Okay, now over here we have the days of the week, all right, which really puts us in the modulo 7 system, all right, because there are 7 days in a week. And we said that we can represent these days with numbers over here. Sunday representing 0, Monday representing 1, 2, 3, 4, 5, and 6, and then the cycle repeats itself. All right, so I'm going to, for the time being, remove this. So if we are given a problem saying that what if today is a Wednesday, all right, if today is a Wednesday, what day would it be? What day of the week would it be 60 days from today? So let me write that question down here. If today is Wednesday, what day would be 60 days. Would it be 60 days later from today? 60 days later. All right. Now we can find the answer to this very easily using the modular arithmetic. All we need to do is, it's a 60 days, and that's the number 60 that we used here. So 60 mod 7 has a remainder of 4, right? And what is our day? It says we start from Wednesday, which is day 3 in our cycle. All right, so day 3, all we do is from day 3, the remainder is 4. You have to count 4 days. You have to add 4 days to the day 3, which is a Wednesday. So we come up to this table. So day 3, this was our Wednesday. I'm going to write that Wednesday. All right. So from Wednesday, we count 4 days. So 3 plus 4, all right, 3 plus 4 takes us to 0, right? 3 plus 4 is 0. That means what was 0 in our days of the week? 0 represented 4, right? So from day 3, which is a Wednesday, we count 4. So 1, 2, 3, 4. It's a Sunday. So our answer is 60 days later. If today is a Wednesday, 60 days later, it's going to be a Sunday. All right. So this is an example of an application of modular arithmetic, and we can solve, as you saw, we can solve this kind of problem very easily using modular arithmetic. In the same fashion, if they ask you if today is a Wednesday, what would it be 375 days later? All right, you can give the answer very quickly by performing modular arithmetic. 375 mod 7, whatever the remainder is, you count for that many days, whatever the remainder is, you count that many days from that particular day that today is. All right, so we will see more examples of this, but I just wanted to give you a flavor of one of the applications of modular arithmetic. Now that we have understood that in modular arithmetic, the solution is a remainder that comes out after dividing an integer value by another integer value, let's discuss the concept of congruence. Now, in the modulo system, instead of using the word equals, we use the word congruent. And we say A is congruent to B modulo M, where would be an integer value, B would be an integer value, and M would be an integer value again. All right, so A is congruent to B modulo M, written A followed by 3 horizontal dashes. So we don't use the symbol for equals. Instead, we use the symbol for congruent, which is 3 horizontal dashes, and then followed by an integer value, which is a B, and then within brackets mod M. If A and B have the same remainder when divided by M. So what this expression tells us is that A and B are congruent provided when each of them are divided by a value M, they will give the same remainder. All right, they will leave the same remainder. So to use a concrete example, let's do this here. The expression in general terms is A and then followed by 3 dashes, B, and then within brackets mod M. So let's come up with values for A, B, and M. So let's say I use the number 50, and then congruent symbol, and then I'm going to use the value 1 for B, and then mod 7. All right, so I'm going to test this out to make sure if this is congruent or not. So 50 has to be divided by 7, and then we are going to check its remainder, and then 1 will be divided by 7 and we will check the remainder for that. So 50, let's perform the division. 50 divided by, this is we divide by the value of m, correct? So if m is 7, it's 50 divided by 7. 7 sevens are 49. We write the 49 below the 50, and the remainder is a 1, right? Remainder is a 1. Let's divide 1 by 7. 1 by 7. And 7 goes into 1 0 times. So I'm going to rub the 0 above. 0 times 7 is a 0. What is the remainder? It's a 1. All right, so both 50 and 1, when divided by 7, left a remainder of 1. So they are considered congruent. All right, now usually this b value, the value of b, should be less than whatever the value of m is. Remember that in modular arithmetic, the remainder can be or will only take values from 0 to 1 minus m. All right, it can take values from 0, 1, 2, 3, 4, 5, 6 only if m, all right, if m equals 7, right? So generally we write the value, whatever value we use for b should be one of these values if m is 7. All right, so it should be less than whatever 7 is what I mean to say. However, if we choose another number like 57, all right, 57 and divide it by 7. Let's do that. 7 times 8 is 56. 57 minus 56 is a 1. That 2 has a remainder of 1. So, which means that 57 is also congruent with 50, is also congruent with 1. All right, but because 57 is a value greater than the value of m, we prefer to keep values for b which are less than the m value that we are working with. All right, let's try to understand what a modulo class is. A modulo class is just a table where we list all the different numbers which, when divided by a certain m value, will have the same remainders. All right, so let's say we are working with a mod 5 system. Right, in a mod 5 system, recall that the possible remainders that we can obtain by dividing any number by 5 would be from 0 to 4, right? So the possible remainders would be 0, 1, 2, 3, and 4, correct? So these are the remainders on the top row, and below these values we can list or group the different integer values which when divided by 5 would have a 0 for a remainder, or a 1 for a remainder, or a 2 for a remainder, and so on. All right, so we will see a concrete example in the next slide for a mod 7 system, but this is just to introduce you to what modulo classes are. It says in any modulo system we can develop a set of modulo classes by placing all integer numbers with the same remainder in the appropriate modulo class. All right, so then it goes on to say that the solution to a problem in modular arithmetic, if it exists, will always be a number from 0 through m minus 1. That's what we just mentioned previously, that the possible solutions, the possible remainders we can expect to get in mod 5 would be 0 through 1 less than 5, correct? Where m is the modulus of the system. What we see here is a modulo 7 class. It is, as you can see, a table where the top row represents all the remainders possible when you divide a value by 7, any value by 7, all right? Keep in mind that whenever you do a division, the remainders will range from 0 to 1 less than whatever you are dividing by, whatever value you are dividing by. So if when we are dividing by 7, the range of remainders would be from 0 through 1 less than 7, which in this case is a 6. If your modulo value is 9, then the set of remainders you can expect after you've performed a division by 9 would be from 0 to 8. It must be 1 less than 8. If not, then the division wasn't performed correctly. All right, so what we have listed, or what they've listed here on the top row, are all the possible values of the remainder. And inside the table, all the other numbers are the numbers which, when divided by 7 in this case, will yield whatever the remainder would be. So the way it works is, these are all the remainder values on the top row. They have listed over below that a particular remainder value all the numbers that when divided by 7 would give a remainder of 0. So 0 divided by 7 would leave a remainder of 0. 7 divided by 7 would leave a remainder of 0. 14 divided by 7 would be a 0, and so on. All right, so 19 divided by 7 would leave a remainder of 5. Likewise, 12 divided by 7 would also leave a remainder of 5. All right, so that's how this table is supposed to be read. So 3, 10, 17, 24, 31, when divided by 7, all of these would end up with the remainder of 3. So they've listed all the values, and this can go on and on infinitely, but they've listed in this table the values when divided by 7 and place them under the appropriate remainder that it would result in. Okay, so it says here every number is congruent to a number from 0 to 6 in modulo 7. For example, 24 is congruent to 3 mod 7 because 24 is in the same modulo class as 3 is. All right, so that's how we should be reading and interpreting a table that represents a modulo class. Let's work through this congruence modulo 7 example first. It says here, determine which number from 0 to 6 the following numbers are congruent to in modulo 7. The numbers they have given us are 60, 84, and 412. So keep in mind we are looking for the remainder after dividing these numbers by 7, and the remainder is going to be a value between 0 to 1 less than 7, which would be a 6. So all the answers that we are going to get should be in the range or within the range of 0 to 6. What we need to do first is take each of these numbers and divide by 7 and look at the value of the remainder. So let's start with 60. So I'm going to do 60 divided by 7. So you divide by the modulo value, which is this 7 given to us. So 7 times 8 is 56, correct? So 8 goes in the quotient and then 56 below the 60, and you subtract what is the remainder is a 4. So the way we are going to write is 60. So this 4 is going to be our answer that we are looking for, the remainder. So the way we are going to write the final answer is going to be 60, all right, 60, and then three straight lines which reads congruent. So 60 is congruent to 4, and then within brackets mod 7. All right, so you have to indicate what you divided the 60 by to get an answer of 4. And that's mod 7. Therefore, you have to write the mod 7. All right, you cannot leave that out. B is 84. So again, let's perform the same division. So 84, let's change the color, 84 divided by 7. All right, so 1 times 7 is 7. That goes underneath the 8. Subtract, we get a 1, bring down the 4. So 2, so 12 is the quotient, and 7 times 2 is 14. So bring the 14 here. What is the remainder? Remainder is 0, correct? So the answer here is the value of the remainder, which in this case is 0, and we write the final answer as 84 is congruent to 0, and then of course the mod 7. All right, 412, again same process. Take the number 412 divided by 7. So 7 fives are 35. Write the 5 here. Sorry, 35 here. 5 is on top as a digit of the quotient. And then this is 6, right? 41 minus 35 is 6. Bring down the 2, right? So it's going to be again 8. 8 times 7 is 56. Subtract. And 6 is the remainder, right? So it's going to be 6 as the solution, as the answer, but the way we are going to write it in proper in the proper notation for congruency is 412, then 3 horizontal lines, and then 6 mod 7. All right, so in the next couple of slides, they are going to perform the same steps, and let's see how they represent the congruence modulo 7. As you see here, they have followed the same steps that we did in the previous slide. So it says 60. They took the value 60 divided by 7. 8, of course, is a quotient, but 60 minus 56, 8 sevens are 56. 60 minus 56 is a 4. That's the remainder. So 60 divided by 7 is 8, but we are not interested in the 8 really in modular arithmetic. We are focused on the remainder. So when we write our final solution, it's going to be 60 is congruent to 4 mod 7. Okay? Likewise, 84 is congruent to what? Mod 7. All right, so let's reveal the answers here. So 84 divided by 7, you have to divide 84 by the modulo value, which is a 7. So the quotient is 12 and the remainder is a 0. So we write it as 84 with 3 horizontal lines, suggest congruence. All right, when there are 3 horizontal lines instead of 2, then we don't read it as equal to. That's only when we have 2 horizontal lines. If there are 3, that means it's congruent to. All right, that's how you read this this notation, this symbol. So 84 is congruent to 0 mod 7. Then 412 is congruent to what mod 7? It's 58 remainder is 6. So the way we write our final answer is 412 congruent to 6 mod 7. Okay. Now we look at a different set of example problems where we use modulo classes in subtraction. It says here, determine the positive number replacement less than the modulus for the question mark that makes the statement true. So in these expressions, we all see a subtraction involved. So first one says 3 minus 5 is congruent to what? Question mark mod 7. The next one says what minus 4, so question mark minus 4 is congruent to 3 mod 5. So we have to replace these question marks with a value, okay, which will make this statement true. So I'm going to go on to the next slide and go through each of these expressions one by one to see how to find the value of the missing of the question mark that they are looking for. All right. So let's go through the explanation on how we should be going about solving this problem. But let me first write the expression, the question that we were dealing with. It was 3 minus 5 is congruent to what mod 7, right? That was the question, and the exercise was to replace this question mark with a positive value. So this question mark will represent a remainder. And remember, the remainders can only take values from 0 to 6, correct? 1 less than whatever your modulus number is. So 1, 2, 3, 4. It can take any one of these values between 0 and 6. Now, when we do 3 minus 5, it's going to give us a negative value. All right, it's going to give us a negative value. But if we keep adding multiples of 7 or multiples of 7, to that value, then we'll always get the same remainder, because multiples of 7 will give us the same remainder of value between 0 and 6, right? So what we do here is in mod 7, adding 7 or a multiple of 7 to a number results in a sum that is in the same modulo class. We want to replace 3 with an equivalent mod 7 number that is greater than 5. We will add 7. So the way they have worked out this problem is to this 3 they have added 7. All right, so they made it like this: 3 plus 7 minus 5. So 3 plus 7 is 10 minus 5 gives us 5. All right, so this modulo 7 is what? Is what we were finding. So 5 is equivalent to what? Mod 7. So 5, when you divide 5 by 7, all right, what happens? This is 0. You write a 0 and your remainder is 5, isn't it? So 5 is congruent to 5 mod 7. All right, so either you can solve this problem by adding multiples of 7 and then performing the subtraction to get a positive value, or what you can do is the other way is do 3 minus 5 is equivalent. This is another way of getting the same answer. 3 minus 5 is minus 2, correct? So we have what mod? I'm going to write the same thing. I'm doing it step by step. So minus 2, if we add a multiple of 7 to the minus 2, we will end up with 5, which is the same as what we got here. So 5 is congruent to, you can do the 5 mod 7, 5 divided by 7, figure out what the remainder is. It's going to be a 5. All right, it's going to be 5 mod 7. All right, so they do perform the division in the next slide using this method, but let's see what answer they got, whether they got a 5 or not. So here we go. where we are going step by step. So 3 minus 5 is congruent to what? Mod 7. Next step is to add a multiple of 7. So they've added 1 times 7 to the 3 to make the left-hand side a positive value, because otherwise we would end up with a minus 2, which would was fine if we added the multiple of 7 to the minus 2, but this is how they worked it. So 3 plus 7 minus 5 is congruent to, let's see what happens next. 3 plus 7 is 10, minus 5 is what? Mod 7. So you have to divide this 5 by 7 and the remainder would be a 5. So therefore this question mark is to be replaced by 5, and we write the final answer as 3 minus 5 is equivalent, or rather is congruent to, replace the question mark with 5 mod 7 within brackets. Okay. Now part B of the question goes like this. Question mark minus 4 is congruent to 3 mod 5. We have to find a replacement value for the question mark. All right. So what this says is the remainder is 3. So we have to divide, we have to find a value for the question mark, and then when we subtract the 4 from that value, from the value we replace the question mark with, and divide it by 5, then we will get a remainder of 3. All right. Now, if we can make this left-hand side a 3, right? If we can make this left-hand side a 3, then 3 is congruent to 3 mod 5, correct? So if we can somehow say 3 is congruent to 3 mod 5, then that's a true statement, correct? So to prove that, just take this 3, all right, this 3 divided by 5, all right? So 0 times 5 is 0. 0 goes into, 5 goes into 3 0 times. So 0 is in the quotient, subtract the 0 from the 3, and we end up with a remainder of 3, correct? So this is a true statement. However, what should we replace the question mark with, so to make the left-hand side equal to 3? All right, so that would be, think about it, it would be 7, right? If we replace a question mark with a 7, then it'll be 7 minus 4 is congruent to 3, right? If we replace this by a 7, then 7 minus 4 is congruent to 3 mod 5, using the same division that we performed here, right? However, this 7 is a value greater than 5. So what we have to do is we have to subtract a 5 from this 7 to get a value less than 7. All right. So now what you have to do is you have to subtract one multiple of 5 from the 7. So 7 minus 5, all right? So 7 minus 5 is 2. So 7 minus 4 is the same as saying 2 minus 4 is congruent to 3 mod 5. All right, so the question mark is to be replaced, since we are looking for a value which is less than the modulus number. We have to subtract 5 from the 7, and the answer that should be given is 2. So here it says we want to replace a question mark with a number less than 5. Less than 5. We need to determine what number less than 5 the number 7 is congruent to in mod 5. If we subtract the modulus 5 from 7, we obtain 2. Thus 2 and 7 are in the same modular class. They will have the same remainder. So question mark is to be replaced by 2. All right. So let's look at the steps that they perform here to find an answer for the question mark. So we started with this expression, question mark minus 4 is congruent to 3 mod 5. But we have to find a replacement for the question mark, and the final value of the question mark should be a value less than 5. All right. So we start by plugging in a value for the question mark, which will make this side, the left hand side, the same as what the remainder value is. All right, so if it is the same as the remainder value, then that would make it congruent. It would place it in the same class. All right, so 7 minus 4 is 3, right? So that would make, so if we use here, if we make this, replace the question mark with a 7, then 7 minus 4 would make this side equal to a 3, and that would make the expression congruent to 3 mod 5, correct? So let's see what they have done here. They have replaced the question mark with a 7. They have replaced the question mark with a 7 minus 4. All right, just the way we had thought of. And then we need this value to be less than 5, correct? So to change the 7 to an equivalent which would be less than 5, just subtract one multiple of 5 from the 7. So 7 minus 5 is a 2, and that's how they came up with a 2, because this value, the question mark, really had to be a value less than the modulus number, which is a 5, without changing the validity of this expression. All right, so 2 minus 4 would be would be congruent to 3 mod 5. Now in part C of the question, we were given this expression here, 5 minus question mark is congruent, and just let me add another horizontal line, because to imply congruency we need 3 lines. All right, so 5 minus question mark is congruent to 7 mod 8. So we have to find a replacement value for the question mark. So let's see the solution they're giving us. In mod 8, adding 8 or a multiple of 8 to a number results in a sum that is in the same modulo class, correct? Thus, we can add 8 to 5 so that the statement becomes, so let's go to the next slide to see what the statement becomes if we add 8 to the 5. Right? So we're going to add 8 to the 5, and then we are going to find a replacement value for the question mark to get a value of 7 on the left hand side, which should be the same as whatever the remainder value is. So let's go to the next slide and see the subsequent steps. So here's the solution step by step. 8 plus 5, they've added a multiple of 8 to 5. So 8 plus 5 minus what value is congruent to 7 mod 8. So 8 plus 5 is 13, right? So it should come up with 13 minus what value will be congruent to 7 mod 8. So we have to find the replacement value of the question mark, which will make the left hand side uh, 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 say the same value rather as whatever the remainder value is. So let's see what happens next. So we see that 13 minus 6 is equal to 7, correct? So if we replace the question mark by a 6, then 13 minus 6 would make this left hand side 7, which would be the same value as 7. So 7 mod 8 would give us a remainder of 7, correct? So let's see. Therefore, question mark is equal to 6 and 5 minus 6 is equivalent to 7 mod 8. Now let's look at some problems which involves multiplication of modulo classes. It says here, determine the positive number replacement less than the modulus for the question mark that makes the statement true. So 2 times question mark is congruent to 3 mod 5. What this means is 2 times what number when divided by 5 will leave a remainder of 3. All right, that's what it is asking. And this question mark, as it says here in the question, must be less than the modulus, which is 5. So the number that we place for the question mark should be less than 5. All right, so we have to do some trial and error, some thinking here. Like let's do it on the side. All right, so 2 times 2 is 4, right? 2 times 2 is 4. So but 4 is less, sorry, 2 times 2 is 4. 2 is less than the 5. However, 4 divided by 5 does not give a remainder of 3. It gives a remainder of 4, right? So let's go to the next one. 2 times 3 is 6, but 6 divided by 5 does not give a remainder of 3, correct? So let's go move on. 2 times 4 is 8, right? So now take the number 8. 4 is less than 5, so we are good in that respect. It's a value less than the modulus. However, we have to take this value 8 divided by 5 and see if we get a remainder of 3. So 8 divided by 5, all right? 5 is what we are dividing by, the modulus. So 8 divided by 5, 1 goes into 8 one times. 8 minus 5 is a 3. So 4 is the number that makes this statement true. So we replace the question mark with a 4. All right. Likewise, 3 times 3 multiplied by what number? We are going to replace that question mark by a number which, when divided by 6, is going to give us a remainder of 0. All right, so the solutions will follow in the next few slides. We'll go through it instead of me working through the entire problem, but I think I have shown one example with part A to give you an idea how to proceed with this kind of problems. So the solution given here says one method of determining the solution is to replace the question mark with the numbers 0, 1, 2, 3, and 4. So the question mark could take one of these 5 values, but they have to be less than the modulus value, which was a 5, right? It was, I think, 2 times question mark congruent to 3 mod 5, if you recall, right? So it could take any one of these values, and they're asking us to perform a trial and error kind of test to see if the congruency is met. All right, so one method of determining the solution is to replace the question mark with the numbers 0, 1, 2, 3, and 4, and then determine the equivalent modulo class of the product. We use the numbers 0 through 4 because we are working in modulo 5. Let's look at the solution worked out step by step. So the initial problem was 2 times what value, represented by the question mark. We have to find the value for the question mark. So 2 times what value would be congruent to 3 mod 5, right? So which means that 2 multiplied by what value when divided by 5 would give a remainder of 3. Correct? That's what we are trying to find. That's what we are trying to establish here. We want to find a value for the question mark which will make this statement true. So the way they go about it is plugging in different values for the question mark, but those values have to be less than 5. So the possible values that the question mark can take would be only these values: 0, 1, 2, 3, 4. Those are the only values that we can plug in for the question mark, and then we can do the calculation to see if it's coming out true, if the statement is rendered true or not. So they first start with plugging in 0. So 2 times 0 is 0, and 0 mod 5 is a 0 that is not 3, so we cannot use 0 to replace the question mark. Next step, 2 times 1. 2 times 1, we choose this 1 here, and we verify, we test if the 1 works. But 2 times 1 is a 2. 2 mod 5 is a 2. We are looking for a 3 for the remainder. So go on to the next one, which is 2 times 2. So we use plug in 2 for the question mark and see if that verifies the statement. So 4 mod 5 is a 4 and not a 3. Again, we are looking for 3 for the remainder. So let's keep going. The next one is 2 times 3, but that has a remainder of 5. All right, 2 times 3 is 6. 6 mod 5 is a 1, so that doesn't work. The last one is replacing the question mark with a 4. 2 times 4 is 8, and 8 mod 5. So when we divide 8 by 5, do we get a remainder of 3, right? So 1 is the quotient, 5 goes into 8 once, and then 5 ones are 5, minus 8 minus 5 is a 3. Yes, all right. So the solution would be to replace the question mark with a 4. Okay, so that's how we will work through these problems of using modulo classes in multiplication. Let's go on to the next example now, which is 3 times question mark is congruent to 0 mod 6. So we are going to replace this question mark with a value which when multiplied by 3 and then divided by 6 is going to result in a remainder of 0. That's what we are trying to satisfy here. So the values the question mark can take would be from 0 through 1 less than 6. So 0 through 5. So I'm going to list the values here. It could be 0, a 1, 2, 3, 4, and 5. Those are the only values that the question mark can be replaced by. So let's go through each trial. We will start by replacing the question mark with a 0 and checking if that will satisfy this expression or not. So 3 times 0 is congruent to 0 mod 6. So 3 times 0 is a 0, and 0 divided by 6 has a remainder of 6. So yes, this satisfies this expression. We could replace the question mark with a 0, and this particular expression would be true. But we cannot stop here. We have to go through the testing of this expression using all these values, because it is possible that more than one value could satisfy this particular expression. So we are going to have to test out this expression, plugging in all the remaining values from our list. All right, so let's go again step by step. Over here we substituted a 1. So 3 times 1 is 3. 3 divided by 6 is a 3. We are looking for a 0. So 1 does not satisfy the expression, the statement here. So we move on to working with a 2. So let's do that. So 3 times 2. So 3 times 2 is a 6. 6 divided by 6 leaves a remainder of 0. So again, this one now 2 then satisfies the original statement, correct? So which are the ones that we've seen worked so far? 0 worked, 1 didn't, 2 worked, correct? Let's try with a 3. So 3 times 3 is congruent to 3 mod 6, right? 3 times 3 is a 9. 9 divided by 6 will leave a remainder of 3, correct? So 3 doesn't work. Next is a 4. So let's bring up the 4. So 3 times 4 is 12. 12 is congruent to 0 mod 6. So 4 is a solution here. So I'm going to 3 didn't work, but 4 we see is a solution. Finally, we have 5 remaining. So let's bring that up. 3 times 5 is congruent to 3 mod 6. So 5 doesn't work either, correct? We are looking for a 0. So the ones that gave us a 0 for a remainder are 0, and then this one, this one, this one, and this one are possible solutions, 2 and 4. Correct? So the final answer is, final answers are 0, 2, and 4. Now the last part of the question was to find a value for the question mark, which when multiplied by 3 and divided by 6 would leave a remainder of 2. Okay, again, it's the same expression as what we worked before, except that instead of a remainder of 0, now we are looking for a remainder of 2. Now, recall that we had worked through all possible value replacements for the question mark, and the results we got. First of all, the values that we worked with or could work with were 0, 1, 2, 3, 4, and 5, right? Those are the possible values that we can substitute into question mark. And if you look back to all the tests we did with all these values up to 5, you will notice that the remainder was either a 0 or a 3. So none of these values gave us a remainder of 2. And because of that, the answer is going to be there's no solution for this problem. All right? Now, one important fact about modular arithmetic, especially for the operation of addition, is that they are commutative groups. Commutative groups imply if we add two values, 4 and 5, now 4 plus 5 will give the same result if we were to switch the 5 and the 4 and write it as 5 plus 4, right? 4 plus 5 gives us a 9. 5 plus 4 also gives us a 9. So if we switched the values, brought the 5 first instead of in the second position, we would still get the same value. There would be no change in the solution, no change in the answer. The same applies in modular addition as well. All right.